Hi, Brandon.
I was at ISAR over the summer doing research in arithmetic dynamics, and a lot of the material I did there is what's going to be in this talk here. It's going to be very condensed and not the full picture, but it doesn't matter. Okay, I'm going to start all the way on the left with a definition. Also, if my handwriting is like too bad, you should tell me. You should really fine. So we're going to define a group, right? Okay, so a group, first and foremost, is a set, right? Let's call it G. And there's an operation.
We can't see you.
Oh, is it too far?
Yeah.
Okay. So I'll just be right over here.
Are you using nice straw or are you using
I just picked up a piece of stuff.
you want
Can you
nice
zoom
straw?
in?
I really am partial.
Yes.
So it's a set G, and there's some operation, right? I'm just going to use this dot because this is easier for me. That takes two elements in G and gives you something back in G, so it's called a binary operation. So let's take like A, B, and C to be elements in G. So what we want is that A times B, I'm just going to say times, it really doesn't matter. Like I could call it plus or whatever I want. We want this to be the same as A times. So this is associativity. I'm going to use a lot of shorthand, by the way. And then for all A in this G, there should be some identity, right? We're going to call it E, so that A times E is E times A. It just gives you A. If you've never seen a group before, you can think of like, if I'm like adding numbers, right? Then 0 would be the identity here, right? Because if I add 1 plus 0, I'm going to get 1. If I add 3 plus 0, I'm going to get 3, right? And so forth. And also, for all A and G, there's an inverse of A and G, which is to say, I'm going to write over here so it's a little bit bigger, easier for me. So it's A times A inverse is A inverse times A, and this is just E. So again, if we're thinking of this adding thing, then we can talk about like 3 has its inverse negative 3, right? Because when I add them together, I get the identity, which is 0. Okay, and we call this group, I'm going to write over here because I want to use that word for something else. So this is just another definition. So group is abelian or commutative. This is abelian is just historical notation. I don't really know why we still use it, but we can say that with a lot of words in that. If we take every A and B and G, we want A times B equals B times A. Most groups are not abelian. The easiest one I can think of is just take a group of like some arbitrary square matrices. Then matrix multiplication is not commutative. But this does form a group. Okay, so this group, whatever stuff, I'm just going to leave that there so you can absorb the definition into your brain. I'm not going to talk about it.
Like,
Even if the first day is like A times B equals B times A.
Yeah, that's just by definition, that's what the identity does. So it's sort of like with the matrices, right? Like the identity matrix exists, right? For 2 by 2 is just 1, 0, 0, 1, right? So it's like if you multiply it by on the right or left by the identity, you're still just going to get the matrix back. And similarly, matrices, they have like inverses as well. If your determinant is non-zero, and so forth. So okay, now I'm going to define an elliptic curve. This is where things, I hope, get a little bit spicy. Because this is just like some boring abstract thing, right? So an elliptic curve, we're just going to write it. It has a standard form. What is it? It's x cubed plus ax plus b. You'll notice there's no x squared term here. That's because for every single elliptic curve that does have an x squared term, there's always a change of coordinates that gets rid of it. And if you know what this means, for a field of characteristic not 2 or 3, then we can always write it down like this. If we're over a field of characteristic 2 or 3, then the general version of this elliptic curve is really nasty. which is why a lot of algebraic geometry is done in characteristic 0. For p greater than 3, right? And so an elliptic curve, there are pictures of this thing, right? Like this. Oops. That's an elliptic curve. I mean, in like the plane, this is what it looks like. In like over the complex numbers, it looks a little bit different. In projective space, it looks a little bit different. But this is just like your mental model. There's some nastier ones. Like there's one that looks like this. I think this is something like y squared equals x times x squared minus something or plus something. I don't know, just put your favorite number in there. And so, okay, so now I'm going to draw a really big one. Skew axes, right? We're a little bit informal. Okay, so I'm going to put 2 points on this curve. Completely arbitrary, right? Pick a point, or pick your 2 favorite points, P and Q. And this is going to hold it up here. So, okay, for now this is just a curve. But we have 2 points also. So we also have a line, right? It's supposed to be straight. So we know there's this third point of intersection. This is classically known as Bezout's theorem, but you can also just write down the equation for the line, write down the equation for the elliptic curve, and you solve it, you get 3 solutions. So this point, let's call it R, right? Now, what you'll notice is that these elliptic curves, they have this y squared, right? And so I'm going to call this just generally E, right? Because it's E elliptic. And so if I have a point like A, B on E, then because this is a y squared, a negative B is also in B, right? And so what I can do is, for all of these points over here, I can reflect it, right? And so I'm going to like drop this down. This should hit it somewhere over here. And let's call this negative R, right? Actually, let's call this one R prime, and then this one is going to be R, right? And so what I'm doing is I'm going to define P. This is supposed to be like a circle with a plus in the middle, but this is how I write them. I'm going to define P plus Q to be R, right? So you draw the line, you take this third point of intersection, and you flip it. And as it turns out, well, okay, let's, before I say that, you can verify by looking at it, right? This is like pure mathematical intuition. That also Q plus P equals P plus Q, right? And this is clear because the line between them is going to be the same regardless of how you do this. So we know it's abelian. One thing that's really, really annoying to check without some extra theorems is that, in fact, it's also associative, right? You can actually write down these points completely generally and solve this like enormous system. And this is how they did it the first time, like, you know, back in the good old day. I don't know how many years ago that was, but it was like, you know, before they had these big theorems. And so what's happening here is that now it's associative. And you might realize where I'm getting at. But before we get there, so you may or may not have heard of projective space. It's okay if you haven't. But basically what I'm going to do is I'm going to take this elliptic curve and I'm going to add a point to it because it's not good enough yet. Let's say we just go all the way out, right? Like past the 5th floor, like past 9th floor, the chem building, like whatever, we're going all the way up. I'm going to add a point at infinity. And it's sort of, in your head, you can picture it exactly what it sounds like. It's just all the way out. And I'm going to call it the script O. And so O is sort of going to act like a base point here. When I say base point, I mean it's like for when I eventually convince you that this is in fact a group law on the curve, O is going to be the identity. Which is to say that if I add any point to O, right, then I'm just going to get the point back. So what exactly should we expect it to look like? Well, what happens if I take this point over here, right? Let's call this S, and I draw this line. Like I add S to itself, right? It's just going to go all the way out, right? So in fact, it's actually going to hit O. So what I'm trying to tell you here is that S plus S is just the identity, right? And more generally, you can define this like because if I add this point to itself, that's kind of funky, right? Because it actually hits these 2 points. That's not really well defined. But, okay, anyway. So, alright, so we have this identity, and we have an inverse too. Yeah, so the inverse is pretty simple. If you just take R and then you take its reflection, you can see when I draw the line through them, I'm again just going to get the identity all the way up here. And so, big fact, right? This is a group law on the elliptic curve. So okay, so our elliptic curve is now not just a curve anymore. It's also a group, right? And this is like pretty strange because we don't normally think of adding points on the curve. But what this type of structure is called is an abelian variety. So what does that mean? There's big words, right? Nobody really knows what that means. I mean, abelian, you know what it means, right? It's commutative. We saw that. It's p plus q plus q plus p. Well, it's a variety. Classically, a variety is the solution set to some system of polynomials, or to some set of polynomials. And so this is just a singleton set, right? It's just the solution to this polynomial, and it also happens to be an abelian group. If it wasn't abelian, then you would call it an algebraic group. So it's interesting how like the sort of the terminology changes. But that's not, yeah.
So all the elements in this defined group are just the points along the elliptic curve?
Yeah, exactly. This exact curve is a group.
Does that also translate to higher dimensions?
Well, okay, so you can realize the elliptic curve as the quotient of the plane modulo some lattice, where I don't want to spend too much time because this generalization, this is like how you generalize it for abelian varieties, right? So if I take the plane, right, and let's say I have like some lattice, so this is just going to be 1, it's going to be like I, right? Because it's a complex plane, right? And so this would be like 2 over here, this would be like 2 plus I, this is 1 plus I, right? And so this is going to just form like this huge thing of squares, right? And if I collapse all of these squares onto this one, right, I'm going to call this one square, I'm going to call it lambda. And so collapsing, like, I'm just going to take this one, I'm going to stick it here, I'm going to take this one, I'm going to stick it here, and so forth, right? So sort of this origin, right, for this square is sort of like this point, but for this square. And so what I'm doing is I'm identifying the origin of all these squares to this one point, and so forth. I'm doing that for every point in every one of these infinite squares. And so this C mod lattice, what this actually is just this single square, right? But what happens when you have a square? Okay, I can identify these two sides, right? And I'm going to get a cylinder, right? Now what happens when I take the two ends of a cylinder together? I get a torus, right? So this actually is C mod n is actually a torus. And the mind-blowing fact is that there is a map from the torus to the sphere given by the it's the Weierstrass P function. Now the reason the Weierstrass P function is special is because it satisfies P prime squared equals 4P cubed minus G2P minus G3, where G2 and G3 are special constants. They come from the power series for P. I'm not going to tell you what P is. But the point is that this is a differential equation, but if you send P prime to xy, you get an elliptic curve. So what I'm trying to tell you is that elliptic curves over the complex number are literally just like, they're all donuts, right? Why does this matter? It's because we got the donut as the quotient of the plane modulo lattice. As it turns out, every single abelian variety, no matter how many dimensions you have, is the quotient of an ambient-based modulo lattice. So that's how you would generalize. I may have gotten way too technical than I intended.
It's actually pretty cool.
Yeah,
But-
that sounds pretty cool. Even
Yeah.
barely grasping it.
It's fine. Basically, like, because there are many ways to think of like how you would generalize an elliptic curve. But if you just want to think of the abelian variety structure, then this is how we can think of an elliptic curve as really just a torus, right, over the complex numbers. And every other abelian variety just has a similar structure. Like it's the quotient by some lattice. But okay, I hope I somehow answered your question.
Yeah, I think.
Okay, and okay, so over here, we saw that when we added S to itself, we got the identity, right? And so since S is an element of this group, this is sort of like saying S has order 2 as a group element, right? We can also think of So I'm going to define something. So the order of some group element is the smallest number n such that s to the n gives you identity. Where s to the n is like s, right, n times. Right? And so you're just like applying this operation to s n number of times. So over here, we saw that we only have to add s to itself once to get the identity. So maybe you might want to ask like what the ordered 3 points are. In fact, you can actually work this out algebraically. The ordered 3 points are the inflection points on the curve. And so like these very algebraic notions have like direct geometric interpretations, which is why like being in the Dealing variety is very nice. It's like you can picture everything. It's all very computational. And so okay, now I'm gonna move on to something that at first glance is going to seem completely unrelated. So this summer, I wasn't. I'm sorry.
All points are of order 2. Is that true?
No, just those points such that when you add them to themselves, they're order 0. Like you saw that like.
There are points that have like a tangent that doesn't intersect the curve itself.
Oh yeah, sure. Like the inflection points, right? Those have order 3.
No, I'm talking about order 2. So the points that if you draw the tangent, it doesn't intersect the curve. That's those points.
Oh
are
yeah.
Order 2.
Yeah, because then if it doesn't hit the curve, it has to hit the point at infinity. Yeah. So this summer, I wasn't actually studying arithmetic geometry as much as I would like to have. I was studying arithmetic dynamics, and part of my goal in this talk is to talk about dynamics. And so first, I have to define what that means. So we're going to start with just a set S, right? S could be anything you want. But it has to be a set, so it can't be your advisor, right? And we're going to start with a function f that takes s to itself. The pair fs is a dynamical system, right? And the reason we care is because we can apply f as many times as we want to something in s, and we're just going to stay in s, right? So that's where this notion of, that's like why we care about this notion of iteration. So we have this example of elliptic curves, right? And so we can actually think about this as a dynamical system, right? This sort of gives us a notion of like multiplying points on the curve. It's like, what's going to happen if I keep applying this thing, right? We can sort of like trace out how these points look on the curve.
Sorry, the set S is going to be what?
The elliptic curve.
Okay.
Yeah.
And F is the group operation.
Yeah.
So, what is this map F here?
Oh, you just add the point to itself.
Add the point to itself. Okay.
Yeah.
So double it.
Yeah, sure.
Okay.
Wait, hold on, didn't you say most of the points are order 2 though?
No. He said most of the points have order.
Oh, okay.
The only points that have order 2 are the ones whose tangent line doesn't hit the curve.
Oh, okay, yeah.
Which from the picture you can sort of, like, for this elliptic curve, it would just be this point, right? But for this elliptic curve, there's 3 of them, right? Because it would be here, here, and here. And so, yeah, so the doubling map is like super important. They give rise to what are called Lattice maps, which are like this huge class of maps that are very unfortunate counterexamples to many big theorems in arithmetic dynamics. But, okay, yeah, so what this is basically doing is it's sending a point, it's taking a point and it's sending it to p plus p, which we're going to call 2p, right? And so this is generally the way you denote it, right? Because you can actually send it to, for example, p plus p, right? And so forth. And so the map is usually just denoted like this. And this is called multiplication by n, where, right, this is just going to be 3p and so forth. And so now I'm going to define something else. I have a bunch of time. You know, I thought I was doing really badly on time, but it's not as bad as
Okay, since you have a lot of time, could you draw a trajectory of a point?
I'm sorry?
Like draw out the trajectory of a point on an elliptic curve. Just to show us an example. Where does this point go?
See, that's interesting. I've never really thought of this. But, oh yeah, here's the eraser. Okay, I'm gonna erase this picture and draw a nicer one. You have to understand though, like, this drawing a picture thing is entirely dependent on my artistic ability as a mathematician. Okay, so I kind of. There we go. Is that good?
Okay.
Right, where would you like the point to be? Which quadrant? No, pick one.
Second.
The second one, okay. So, oh man, this isn't curved enough. That's better. That's a nice curve. So I'm going to pick,
Or maybe just show the order 3 one. No.
the order 3 one.
Yeah.
I believe the inflection point would be like somewhere around here. What happened?
I believe that.
Yeah, so, I mean, if my picture was correct, it would land on the curve,
Okay.
but it's not correct. I told
Well,
you.
it just lands down.
Well, that curve's going to negative infinity, so it'll eventually,
I'm sorry?
since the curve's going towards negative.
Well, it's asymptotic, right? Like, at infinity, right? It's like, if I have this point over here and I draw the tangent line, right? Then it's like, this is going to negative infinity and this is going to positive infinity, but the operation still only gives you like 1 point, right? Sort of when we're adding this point at infinity. Okay, one actually really nice way to think about it is this is the plane, right? And I'm like identifying all of the infinite rays as having the same endpoint up here.
Okay.
It's like you're like folding the plane up to be you add this 1 point and now you have a sphere.
I thought you said it was projected plane.
I never said plane.
Oh,
It's in space.
no, I thought it was in the projected plane, not the sphere, or is it?
I don't understand the question.
Oh, okay.
No, this, like I do this,
Projected,
like the curve-
that's all.
like elliptic curves naturally live in CP2.
Oh, okay.
Yeah.
That projected plane, not that.
But yeah, so that's why.
No, I think what it was asking was that like, you're adding 2 points and you're getting a third point, which is negative infinity.
See, but it doesn't have to be negative infinity, because I could just go back out the other way.
Or
Right.
positive infinity.
Yeah. But my main
That's
point
not
is
what it
that it
is.
should be something else on the curve that isn't infinity.
Yeah.
Right, yeah.
But my picture just is really bad. I don't
Because
know.
your infinity is your identity, right?
Yeah, like if I take this, right, this is a better one, and I draw the tangent line, you see how I get this thing,
Yes.
right? And then if I draw the tangent line to this again,
Don't you want to reflect that first?
oh yeah, you're right. Oh, you're so smart, actually. Right, so let's go over here, right?
Yeah.
And then we draw,
So that's the point that's 2 times the original point.
yeah, so this is P, this is 2P.
Yeah.
And we can draw the tangent line to this. Oh, let's just call this P prime. And
No.
then we're going to reflect.
Don't you want to do 2p plus p now?
No, because we're just sending P to 2P, right?
Okay.
And then, so what we're doing is, it's like,
Like these right?
Okay.
yeah. Oh, what's up? Nice hair. Yeah.
Alright.
So you apply the function to the output, right? What you're describing would be the tripling one.
Okay.
And so yeah, then we draw this, and then we reflect over here, and now this is 2P prime, right?
Or
Which
4p.
Sure. You can call it whatever you want. Yeah.
2p plus 2p wouldn't necessarily be the same as p plus 3p, right?
It should be, right?
Well, yeah.
It's associated.
Yeah, exactly.
Oh,
Yeah, because, right, it's group law, so 2p plus 2p, this is really just p plus p plus p
yeah.
plus p, which is 3p plus p. Right? Wait, does anyone have any more questions before I talk more about that? Yeah.
So then what's the order of that point? Because you said 4P before.
Well, I don't know. If you pick an arbitrary point, it's generally like, I have no idea how you would guess the order. Yeah, I mean, well, this is something, that's something, the order of the points,
Right.
that'll come up more in a little bit.
Okay.
Okay. So, yeah, so this is one way, we actually think of the elliptic curve as a dynamical system, which is really cool because it's not really something you would expect to associate to it. So I'm going to define some more words now. So a point is periodic, right? And this is just for general f and z. if some iterate of it just brings it back to itself.
So it goes in a cycle.
Yes, correct. Yeah.
So some iterate, not all iterates, right?
Well, if one iterate of it does, then so does every multiple of it, right? Then like f to the n raised, f to the 2n, f to the 3n, they're all also going to
Well,
bring it back.
it's that there's a specific z. It can't just be any number, right?
What-
For each
Are you
function,
talking
there's.
about n or z?
I'm talking about z.
Yeah, the point, yeah, z is periodic.
Okay.
So, yeah, so this is a property that belongs to the point. Under this specific function, right? It might not be periodic under some other function.
Yeah.
Right, like x squared. Yeah,
What if it refers back to itself at decreasing frequencies?
I don't know what that means.
So say the 4th iteration, then the 20th iteration, and the...
You can't have that. Because if the 4th iteration brings it back to itself, then
Oh,
so will
yeah,
the
it
8th,
goes-
and then so will the 12th. But there is a weaker notion of being periodic, which is preperiodic. And this is saying that f to the n equals f to the m, right? So this picture looks like this, right? Where we're going in a cycle. What this picture looks like is you go here and then you end up in a cycle, right? So there's like a tail. So you might have to iterate a few times before you get something that is periodic, right? And so the reason I'm defining this thing is because having order 2 is the same as having period 2, right? Because, or I guess it would be, no, that's different. I'm sorry, I misspoke. Yeah, because I guess period 2 would be like if p plus p equal p, right? And yeah.
Are the orders of points necessarily finite?
Well, yeah. I mean, how do you, like if f to the n is, like if f to the n of z is never z, right, then like you can't even define order. Actually, this is called a wandering point if it's not either of these things. Like an example of this is if you take, if you send z to z squared, and then you go to z to 1.1, it's never going to go back there, right?
So is the period going to be the order plus 1 because the order brings it back to the identity, and then if you add it one more time, it'll bring back to its original space?
You mean for this order 2 point?
Yeah, I mean for like any order n point, if you add it to itself n times, it'll go to the identity, and if you add it one more time, it'll go back to where it was, right? Because the identity plus...
Well, see, it's a little bit different there because what you're doing is like after... Well, that depends on really like the math you're talking about. Because this plus, like you're doing p plus p, right? And then this gives you some p prime. And then the next thing you're doing is p prime plus p prime. You see? And so this is why it's like, I really should maybe have written like an n down here that tells you like how many times to add. Yeah, and then, so like if you have this multiplication by n, and then you have a point of order n on the curve, then the first iterate is going to be identical, right? That's what's called a fixed point, because immediately you're going to have f of z equals z, right? And then everything after that, or no, f of z is not going to be z. I'm being silly. F of z there is actually going to be the identity. Let's just say like 1. Yeah, this periodic stuff on the curve is a little bit hard to picture because you want something that satisfies this, right? And this, we're not entirely sure where it's supposed to go. Or like, what point to pick to satisfy this. Yeah, I'm not so good with the artistry stuff. I'm sorry about that. Are there any more questions? Okay, yeah.
For the preperiodic, when it goes into that, so like you have the first point on the left and you have the second point in the middle, and then it starts looping in that circle and it never goes back to the first point?
Correct.
Okay.
Yeah, because once it's in the circle, it's never going to get out.
Okay.
Right. That's
Just
what
wanted to make sure.
Yeah, no. That's like this notion of being periodic is that it's like stuck, basically. And then once you know it's periodic, it's like, you can basically just talk about these 3 points, because you're never gonna hit anything else.
Yeah, so like we just don't care about that.
Yeah.
You said we don't know points that can be periodic in order to, right?
Well, the order 2 points you can describe, right?
Or the p plus p equals p.
I mean, when I said we don't know, I meant like, if you just stare at an elliptic curve, picking a point that satisfies that might be a difficult thing to do, right? Because like, visually, it's hard to think about like where these points are going to go, and sort
But
of.
we can get a computer to do it?
Oh yeah, sure. I mean, you can do it by hand.
And then tree, for example, would be infinity, right?
Oh yeah, sure. Like the identity. But so, I mean, yeah, like if you give these points like just abstract coordinates, you can just work this out like high school algebra, right? If you just start equating everything, it's going to be really messy, but you can do it. Yeah. When I said that, I just meant like a priori. So okay. I guess now I'm going to talk about the meaty stuff, because up until now I've sort of, I don't know what it seemed like, but I've just been trying to build up like the basic definitions and ideas. So we're going to let E be an elliptic curve again.
Just grasp the basics.
Yeah. So we're going to let E be an elliptic curve, and we're going to let P, which has coordinates x and y, be some point on the curve, right? So let's say, let's take one of my favorites, 4x cubed. What this number is doesn't matter. What's really cool is that this is the elliptic curve associated to the lattice, to this lattice. That's why we're so let's say we want to find points on here, right, x and y, such that x and y are both rational, right? We want them both to be fractions. How do we do that?
Is G2I
It's a number. Yeah.
Oh,
Yeah, it's just some constant.
yeah, okay, you're still.
I'm sorry?
I will just make sure if you're still real number.
Yeah, sure.
Can you repeat the question?
So we have a point xy on this curve, right? G2I, I'm just going to, let's say 7. Right? How do we find rational points on this curve? Yep. Or, you know.
No, sorry.
Does anyone have any ideas?
I have a question. Is that thing next to the x, is that a 4 or a 1?
That's a 4. Okay. Well, there's one easy one on here.
0,
Yeah,
0.
yeah, no, this is true, this is true. 0, 0 is like, that's right. That's good. Does anyone know of any others? Okay, does anyone know if there might be finitely many or infinitely many? If there are finitely many, how many do you think might be on here?
5,000.
Yeah, you see, I have absolutely no idea. This is just some random with the curve. Right?
Wonderful.
Yeah, the answer is, I have no idea. I mean,
Why wouldn't it be 3 though?
what do you mean, why wouldn't it be 3?
Like, just because x to the third.
No, the question is why would it be 3? If you think it's 3, then you need to give a
Yeah, you
proof.
gotta prove that.
Yeah, can you
Okay, that's
can you find 2 more rational points on this curve?
I'll let you know.
Okay, no, I'll be there.
What's that all that, you know?
So, we're going to let, alright, so by this notation, I'm going to be talking about the subset of rational points on this elliptic curve P, right? In particular, this is a subgroup, which just means that as a set, it inherits the group operation.
Why is it closed?
Why is it closed?
Yeah.
Okay, just add 2 rational points, right? You can, like, everything you're doing is just like linear equations or some sort of.
Okay, yeah, so you have 2 rational points, so the
Yeah.
line between them has rational slope.
Yeah,
So then you get another point, but you don't know why those coordinates are rational.
you can work it out algebraically. It's just like, again, this high school algebra manipulation.
Cool.
It will be rational, I promise.
Alright.
And so again, it can be infinite, it can be finite. We really don't know. We don't. Okay, yeah, but so the one thing we do know, and this is originally it was just Mordell's theorem, but it was generalized by Fay. So this says that the subgroup is finitely generated, right? What this means is that if I take like some finite number of rational points on my curve, and I start adding them together, I will get every rational point on my curve. The really cool part is that we can actually explicitly decompose this. This is, so z is the integers, right? We're going to raise this to some r, and then we're going to take the direct sum. So when I say torse, right, this is the torsion subgroup of this thing, which is just the finite order points, right? Because rational points don't need to have like finite order, right? But some of them do. And so this is like an amazing decomposition. This is like a pretty good result. And this R, this is called the rank. We have no idea what the rank could possibly be. The current largest one we've ever, or math has ever found is 28. The guess as to whether it's bounded or unbounded has fluctuated over the years. We still don't have a conclusive answer in any case. This this torsion subgroup, there actually is like a huge theorem about this. This is due to Mazur, who I think is still at Harvard.
Yeah, he is.
Yeah, there we go. So this, the finite order rational points, this is less than 16. And it's never 11. Yeah, it hits everything. I think it's either 16 or 14.
So, okay, so what
yeah.
you're saying, like, the number of points on your elliptic curve that return to
The
themselves.
finite order rational points.
Yeah, the number of rational points on the elliptic curve that return to themselves.
Yep.
That number is less than 16.
Yep.
But not ever 11.
Arbitrary elliptic curve.
Why isn't it never 11?
I don't know, read the proof. I don't know. Well, we know. There is another theorem due to Siegel. Oh, by the way, Mordell-Weil, that theorem, in addition to the following theorem that I'm about to write down, which is due to Siegel, in their full statement are much more general than I'm writing them down. If we take just the integer points, this is not a subgroup anymore, this is just a subset.
Okay.
If we take just the integer points on the elliptic curve, this is always finite.
Okay.
Don't ask me about how big it is.
That makes sense. I don't know.
Honestly, I haven't memorized. I haven't memorized. And there's one more finiteness result. And this finiteness result, which is also, like I'm not stating in its full generality, is probably what I think is the most important one. But that's just my stupid opinion. This is Fulton's theorem. So I said before that every elliptic curve is a donut. As it turns out, for general plane curves that might have some sort of higher degree, we can like identify them with a donut, but with a bunch of holes, right? Like 27 or something. Or 2, right? 2 is actually the magic number. Because so the number of holes, that's called the genus. And if we have genus greater than or equal to 2, then we immediately get finitely many rational points. This is a big deal. Now again, you might ask me, well, how many do we have? Not constructive at all. We don't even have a good upper bound in general. We don't even have a good algorithm to find them. But that's okay, because I have 20 minutes left. And
Find them now.
so you might wonder, like,
It doesn't apply to elliptic curves because
elliptic curves have genus 1, right? So they only have one hole. But they might still have finite many rational points. What this is saying is that for every curve that's a 2-hole donut or more holes, will always have finitely many rational points. Yeah, so the number of rational points on the curve is actually related to that rank somehow. But anyway, so now you might ask me, why am I talking about dynamics? And why am I talking about elliptic curves? And more importantly, why did I just mention like 4 theorems from arithmetic geometry that seem completely disconnected from everything I've mentioned so far? Well, this is a fantastic question.
Because the lecture is on arithmetic geometry and dynamics.
Well, yeah, but why, right? Like, you haven't really seen anything there. So consider the following problem. I'm going to take a function f and a point z, right? This is a function, this is a point. And I'm going to consider all forward derivatives of it. So what I'm doing is, I'm taking the point, I'm applying f, and I get something. I'm going to apply f again, and I'm going to get something. And I'm going to apply f again, and I'm going to get something. And I'm going to keep applying f for every n greater than 0. Sometimes this might be finite. For example, if f is periodic, this is going to be finite, because it's just going to stay in those same couple of points. If f is preperiodic, this is going to be finite, because it's going to have a tail, and it's going to stay in those same couple of points. So this is called the orbit of z under f, or I'm using the script O. The script O has like 500 million goddamn uses in math. I don't understand why. Like, but okay, so it's called the orbit. And so we might wonder. So, okay, so let f be some rational function, which means it's a polynomial divided by some other polynomial, right? Let's let both of these polynomials have coefficients only in the rational numbers, and let both of them be in the single variable z, right? So this is called a rational function with rational coefficients. So I'm going to let f be one of those, and I'm going to let z be a rational point, right? So how many rational points do you think I'm going to have in this orbit?
11.
Well, infinitely many, right? Because if I put a rational point into a polynomial, I'm going to get a rational point out.
Yeah.
And if I divide two rational numbers, I'm going to get a rational number, right?
Okay.
So this is like a stupid question. How many rational numbers are here? Well, let's think of like a good question, right? No, I mean really, you sounded offended. Well, because people have to ask it at some point. So how many integer points are in this orbit? That's interesting, right? Okay, well, for example, if I take a polynomial up here, right? Let's say z squared plus 1, right? And I'm going to divide it by the polynomial 2, right? Fantastic. I have z squared plus 1 over 2. This is a valid rational function. The fact that it happens to be a polynomial is a special case. That's amazing.
Okay.
And so, actually, let's not divide by 2. Let's divide by 1. This is easier. No, well, you're going to see why. So this is our function f. And I'm going to let z be 1 here, right? So what happens when I plug z into here? I'm going to get 3, right? Or no, I'm going to get 2. And when I plug 2 in here, right, I'm going to get 5. When I plug 5 in here, I'm going to get 26, and so forth. So you notice all these numbers are integers, and they're all going to remain integers. And so if f is a polynomial, then if I feed it an integer, I'm just going to get infinitely many integers. So we can throw that out. What are some other stupid cases, right? What if I let f of z be 1 over z, and I let z be 2, right? Then it's just going to go back and forth, right? So again, I'm going to have infinitely many integer points. So what you'll notice here, what the problem here is not that it's going back and forth. The problem is that f composed with f of z is a polynomial. In particular, 1 over z is just z, right?
Mm-hmm.
And so that's really the case, right? Like, what we really hate are polynomials. So let's get rid of them, right? Let's just say if some composition of f with itself gives us a polynomial, we're going to throw it out, right? So how do we know if f composed of itself is ever going to give us a polynomial? Right? That's a problem, because we don't just want to start throwing out good functions. As it turns out, now this is like a really cool result, I think, is that, let me erase some more theorems that you probably haven't read anyway. So I don't know who proved this first. Also, this f composed with f composed with itself n times, I'm going to write it as f to the n. So just note that this, I'm not raising it to the n power. These are different. So if f is a rational function with rational coordinates, and f to the n is a, so this is going to be a brackets, these are parentheses. So this means that f to the n is a polynomial, then already f composed of itself must be a polynomial. So we actually only need to check composition like 12. So like this is all we need to check for it to be a polynomial. Now the theorem, right? Really the analog of Siegel's theorem in arithmetic dynamics says that, I'm going to erase Falsing's theorem, even though I really love it. Right, notice how I haven't proved anything, right? It's because all the proofs are really long, and I only have an hour. Imagine if I had like 30 minutes, Jesus, right? So if f is a rational function such that f squared is not a polynomial, and if z is a rational point, then the orbit of z under f has only finitely many integer points. Right, so again, the rational points we don't care about like at all. But the integer points we do. Right? Okay. Does this surprise anybody? It should. I would hope it does, because like there's no reason for this to be true, right? It's like, why should we expect finitely many integer points? Actually, I do remember that the proof for this actually comes from proving it for the case of complex coefficients first, which is like even stranger, because generally when you're working over like arithmetic problems, you never care about the complex numbers because they're like algebraically close to what can possibly happen. Yeah.
Oh, could you repeat the theorem?
If f is a rational function with rational coefficients such that the second iterative f isn't a polynomial, then the orbit of a rational point under f is always going to contain finitely many integer points. Thumbs up? Thumbs down? Anybody have any questions? I know probably a lot in the back of your mind that you don't want to ask. But that's
Wouldn't it
cool.
be a result of that one?
No, this is such a case.
This one.
Or wait, what's the result of what?
So this one, like if you reverse it, like if you say not 2, then not then you don't have any n greater than 2 that has that becomes a polynomial, right? And
No, I mean, like I could still feed a rational function an integer point and get an integer out,
I see.
right? And like, because the problem is that if some iterative is a polynomial, then okay, maybe the iterative after that doesn't have to be a
It
polynomial,
doesn't have to
but
be-
every nth point is going to be an integer, right? And so then we're going to get infinitely many. Yeah.
So in the case that f2 is element of qz,
Okay.
would that make it so that there is an infinite amount of integer points on it?
Yeah, if any f to the n, right? Because here we're saying we only need to consider the second iterative,
Yeah.
right? Because if I start like if the second iterate is a polynomial and I start listing out the points, right? Maybe this one isn't, but then this one will be because it's a polynomial, right? Or okay, when this one is, right? Because it doesn't always have to be. Like if I feed a rational point into the polynomial, I don't need to get an integer out, right? Well, let's just assume this one is, right, for the polynomial, then this one won't be, but then this one will be again, right? And so you see sort of what the problem is. And in general, for n, it's just going to keep happening. Yeah.
For like a function such as 1 over z, though, like you're just going to be going back and forth between 2 and a half for z.
Yeah.
So like, how is that infinitely many?
Because the number 2 appears in many times. Yeah, okay, I should have clarified. I don't mean necessarily distinct integer points in this orbit. I just mean an integer showing up infinitely many times. Because of the fact that like the orbit could have like it could be periodic, for example, right? And then we would just have the same 3 points. But like if you just listed them out, just in order, right? Yeah.
So these orbits that have a finite amount of integer points from that theorem, do they have an infinite amount of points?
Not necessarily.
Okay.
Like if you look at it as a set, right? Because sets don't have the doubles. But I'm saying like if you just started listing them out, right, then you would get infinitely many integers. Like you could have like some period 3 thing where this one is always an integer, but these 2 are not. And then so you go integer, rational, rational, integer, rational, rational, integer, and then so then every third one would be an integer. Any more questions? Okay, cool. And so there is this enormous conjecture in arithmetic dynamics that was stated by Patrick Norton and Joe Silverman in the 1960s. It's called the uniform boundedness conjecture. And almost every one of these theorems that I've stated that really belongs to arithmetic geometry is the uniform boundedness conjecture as a special case. And the uniform boundedness.
Before you start, so what do we understand from all these theorems about the dynamical system that is built on an elliptic curve? What was the result? You stated that.
Oh yeah, so I guess part of this is showing you that, because like arithmetic geometry is already like an established field, but arithmetic dynamics isn't. And part of the point is that like a lot of stuff in arithmetic geometry you can look at as just belonging to the dynamical part, right? And there are tools in dynamics that we can use to analyze the geometric aspects. Like this, for example, is like a direct analog of Siegel's theorem. And a lot of the ideas in arithmetic dynamics started like as analogs of arithmetic geometry. And in particular, the uniform boundedness, which belongs to dynamics, implies a lot of results in geometry. Yeah. Oh, I think I do. Okay. So we're going to let f be some rational function again with rational coordinates, and let's consider the set of preperiodic points of f. Now the conjecture is that the size of this set is bounded. I'm sorry?
Finite.
Well,
I was guessing.
It's bounded by a constant that depends only on the degree of the rational function, right? This conjecture is more general, but
by degree means the power of c.
oh yeah, I should have said this. The degree of f, which is the degree of say like q of z over q of z, is equals. It's the maximum of the, yeah.
5 minutes.
Okay. Yeah, that's not time. I think, yeah. So this is the big conjecture. This implies a lot of stuff. Like, if you take this map to be like addition of points on the curve, then it might tell you some stuff, right? Because like this addition of points on the curve, it tells you stuff about what's happening. Like as a dynamical system, it tells you about what's happening on the curve. And so part of this stuff is like rational preperiodic structures, right? This is really where this stuff comes in. If I have the map z squared, right? I'll take the point 0, right? 0 is going to go back to itself. Infinity is going to go back to itself. And that's it, right? No, that's not it. 1 goes back to itself, right? What about negative 1?
Goes to 1.
Right, yeah, negative 1 goes to 1. This is called the preperiodic portrait of this function, right? This uniform boundedness conjecture states that for some arbitrary rational function, we can always draw this and can have finitely many points bounded, and the number of points in here is going to be bounded by some number based on this, right? But sort of like, how do we find these things, right? Well,
Good question.
yep.
These are all in CP1, right?
I'm sorry. No, we're only talking about rational points. I wrote down infinity because, like, as a rational a preperiodic point, you generally generally homogenize these rational functions, talk about them in projective space, and then come back down. So, like, infinity, yeah.
So, because we are talking about infinity, would you also have a preperiodic in negative infinity?
Well, infinity and negative infinity are identified in projective space.
Mm-hmm.
They're the same thing.
Yeah.
So, yeah. So, okay, let's take the following function. This is something I worked on for a while. Z cubed plus A over AZ squared. Right? So, okay. So, you notice 0. No, 0 is no good. It doesn't go back to itself, right? Because we're going to divide by 0, right? So 0 is always going to go to infinity. And if we plug in infinity, there's a z cubed up here, but a z squared down here, so infinity is going to stay fixed. But so A here is a parameter, I forgot to say that. So we want to find rational values of A that give us a preimage of 0. But that's easy. We want z cubed plus A to equal 0. Okay, so we want A to equal negative z cubed, right? But we want A to be rational. So in particular, this only holds for rational z. So if I just set A equal to t cubed, right, then the point negative t is going to be a preimage of 0. You can see this because negative t cubed plus t cubed equals 0, right? So boom.
You could have irrational z and rational a.
Well, we want rational point z and rational
Oh,
parameter
okay,
z.
sorry.
Yeah, so that's why, right, like this is a curve and we want to find rational points on it, right? The coordinates of this curve are a and z, right? And so when a equals t cubed. Okay, what about preimages of negative t? And I'm going to just write this down and then stop because I don't want to go too far over the time limit. But this amounts, right, because since a equals t cubed, we can rewrite this as z cubed plus t cubed over t cubed z squared, and we want this to equal negative t. Yep.
So, in the case of a being 0, what would that look like?
A being 0.
Yeah, because that immediately jumps out.
Well, homogenize it, right? It's going to be, if you homogenize this, it's going to be, let's see, z cubed plus ay squared and az squared, right? So if a is 0, then this is just going to be, it's going to be this map on projective space.
So that wouldn't be reflected.
Well, no, right? It's just going to send everything to some point at infinity.
Okay.
Right? Because if you just take like any point x, y, and you apply this to it, it's going to send it to x cubed 0, which you can scale down. You can divide by x cubed. This is the same as 1, 0, right? And 1, 0 is a point at infinity.
Sorry, what did you get? A y squared?
Well, you're homogenizing it to be a projective function. Projective functions have to be homogeneous with degree 3.
Oh,
in every
I
term.
see.
Yeah. So okay, I just wanted to finish up here. So what this gives you is z cubed plus t cubed z squared plus or no, z cubed plus t to the 4th z squared plus t cubed equals 0. This is a curve. It's not an elliptic curve, but it's a curve, and we want to find rational points on it. That's what this whole arithmetic geometry and arithmetic dynamics thing is all about. Can anybody see any on here?
0.
0, perfect. So 0, 0 is on here. Does anyone see any others? Nope. Also, you have to give me 2 numbers, but -1 plus any other number is going to be wrong.
Well, no, because -1 would be -1 plus 1 plus -1, which
You have to
would
give
be...
me 2 numbers. There's
Oh.
a z and a t.
Oh, okay.
Yeah, but I'm telling you you're wrong because, like in the plane, in the plane, right? We can write this as a projective curve, which means that all these things are going to have degree 6, because this one has degree 6, these degree 3. So in the plane, this is the only rational point on it. There is absolutely no way to have guessed that, because we just don't know, right? Like this is a 3-hole donut, which means we know we're going to have finitely many points. But what the hell are they, right? Thankfully, we have Chaboty. He established in the 40s, like very rough early bounds on the number of rational points. We have Coleman, who came around, I think in 1985, and I'm gonna write down the formula. So FP here is gonna be the field of P elements. Don't worry about what that means if you don't know what it is. For a smooth projective curve, X of genus greater than or equal to 2. We have this bound, right? But the problem with this bound, right? Because this is explicit, it's a big deal. The problem with the bound is that it's not always the exact number of points that we have. In particular, if you remember what the rank from before is, we need rank strictly less than genus. That's when Chaboty-Coleman works. It's extremely restrictive. Computationally, it's extremely restrictive because it's really hard to implement. It's only been implemented in Magma so far, which is a computer algebra system. It's funded by the University of Sydney. It's closed source. You can probably get a license if you ask someone here, because we're a university, we should get licenses as students. For the case R greater than or equal to G, there are papers being published on this like in the last couple of years. Jennifer Balakrishnan at Boston University, Natan Dogra, I think at Oxford or Cambridge or something, and Min-Young Kim at some big name school in France. So they're doing what's called non-abelian Chabotier. Because really what the Chabotier method is doing is, for every one of these curves x, you can embed it into like some abelian variety that sits all the way up here, called its Jacobian. And it's a lot easier to study the rational points on there. And then by knowing the rational points up here, you get information down here. But Jacobian is an abelian variety. What non-abelian Chabotier does is look at like non-abelian geometric objects called Selmer varieties associated to this curve. And you get like this infinite sequence, and there's a bunch of conjectures, there's a bunch of work that would probably take me like a few hours to explain. But okay, thank you.
Anyone have any remaining questions?
Yeah, I know that was a lot, like, I'm sorry. Yeah.
Hey, can your elliptic curve be singular and it still work?
Oh yeah, it doesn't matter. Okay, so every curve, right, every affine curve has a projectivization. When you're in projective space, you can normalize to a smooth model, and to every smooth projective curve, you can associate a Jacobian. So it might take you a couple steps, and the information Chabotier gives you is going to be about the smooth projective curve, but if you just work backwards, it's not perfect.
Yes, okay, yeah, just
But
everybody,
yeah, so
in case you didn't already sign in, because you want to show proof that was
it's not as for super elliptic, we only have that.
No,
Yeah.